That gives you 3/4 of an hour to have a shower. We all hope that the weather will improve because it will be an outdoor reception, but we'll see afterwards. Okay, now we'll commence to this session. Well, up to a few years ago, the bottleneck was always the network, so it simply helped if you could add some more bandwidth to the problem, and that solved it usually. But this is no longer true, and problems appear in other places. Mirko Benz will address this issue of endless implementation in his paper, and also will show the way out of it, I hope. This talk is an architecture and prototype implementation for TNC2001 hardware support. Mirko Benz received his diploma in computer science in 1997, where he is currently working towards his PhD. His special interest is the analysis and efficient implementation of transport layer protocols, including hardware support.
Thank you, Mr. Chairman, for this kind introduction. Ladies and gentlemen, in my presentation I would like to describe an architecture and prototype implementation for TCP/IP hardware support that was developed as a chair of computer networks at the Dresden University. First of all, I would like to say some words concerning motivations. Here I would like to draw your attention to the major points. These are at first demanding services. Services like switching, routing, quality of service support, or internet security provision require tremendous processing power. As we go up the protocol stack towards the application layer, then naturally the application complexity increases as well. So we have simple services like switching, where we need only around 100 instructions to process a single packet. However, for internet security, we need more than 1,000 instructions to process a single packet. So somehow we have to provide this processing power. The second point that I would like to raise here is the difference in the growth strength between processing power that is available and the networking bandwidth. According to Moore's law, we have a deficit of processing performance around every 18 months. However, networking bandwidth increases much faster using the gigabit Ethernet, 10 gigabit Internet, and so on. And therefore, we have a growing gap between bandwidth that is available at the networking layer and the bandwidth that can be actually used by applications. And because of these two issues, demanding services have to be supported somehow, and this growing difference in the trends of processing power and networking, we thought that it's a good idea to think about hardware support for protocol processing acceleration and to do a case study for the TCP/IP protocol. Let me first give you a brief project overview. Protocol processing acceleration with hardware support is a quite complex thing to do because it requires computer science background as well as electrical engineering background. And therefore, we restricted this part. And therefore, we restricted this task. So what we do is to first have a look at one specific class of networks. These are local area networks, for example, gigabit Ethernet. Here we have two important properties, like relatively high bandwidth and very low error probability. But if you think in the future and consider optical networks, for example, then these two important properties will also be through provider networking. And the other thing that we considered were to restrict our work on development and improvement of host implementations only. So routers and so on are beyond the scope of work. There are quite a number of steps required to achieve hardware support for protocols. We started with a protocol analysis and then did the hardware software partitioning and afterwards the system simulation. The next steps consisted in developing various hardware prototypes, evaluation of these prototypes, optimization work, and finally integrating them efficiently and transparently into today's operating systems. So with our project we had two major goals. The first one was to develop a flexible protocol engine that can be adapted towards specific requirements, and the other aspect was to develop a domain-specific methodology to achieve hardware support for complex transport layer protocols, and not just for TCP, for example. In my talk, I would like to first address protocol performance issues concerning TCP, and then describe our acceleration approach in more detail. Afterwards, I would like to introduce the simulation environment that we built. Furthermore, in this context, I would like to have a look at operating system integration of this acceleration approach. Afterwards, I would like to outline the hardware implementation directions that we are working on and discuss one of them in more detail before concluding my talk. Let's start with protocol performance issues. The figure on the right side shows the typical implementation architecture for implementation of the TCP/IP protocol. As you can see, we have main layers like application, socket, TCP protocol, IP protocol, network driver architecture, and the actual network. From this highly layered architecture, quite a number of potential optimizations, potential overhead categories arise. These are, for example, communication overhead, synchronization overhead, as packets have to travel through each of these layers. Furthermore, we have operating system call overhead, we have potential overhead due to copy operations, then data has to be transferred from the application user space to the operating system in kernel space, and so on. So there are quite a number of potential overheads. All of these overheads can be categorized as per byte or per packet overheads. So if you want to improve throughput, then you have to take a look at the byte overhead, and if you want to decrease latency, then you have to look at per packet overhead. Developing optimized protocols and doing research in this field is not a new thing, and therefore quite a number of optimization approaches were developed. For example, interrupt suppression, security mechanisms, user-level networking, or simple kinds of hardware support like checksum offloading, for example. Or another aspect is, for example, to extend the frame size within the network. However, although there are a number of optimizations, the performance of today's TCP implementation within normal operating systems cannot be achieved. We see here throughput measurements with a TCP stack on the Linux operating system, which is lower Graf. We achieve only about 330 megabits, and here we have used a gigabit network and a relatively fast PC hardware. On the other hand, so-called line-based protocols that are specifically optimized towards a network, in this case Murinet, can achieve performance levels within the gigabit area. So it's possible to achieve these levels, however, with several drawbacks. For example, these so-called line-based protocols are often very limited in their applications. For example, they are not compatible, obviously, to the internet. And therefore, our main goal was to improve protocol processing performance. But there are other goals as well. For example, we wanted to start with a software implementation as a foundation and gradually integrate hardware support on an as-needed basis. Furthermore, obviously, for an internet protocol, we wanted to achieve on-wire compatibility. And as potential end systems are very diverse in their architecture and their requirements, we wanted to have a look at very different implementation architectures, ranging from software to hardware. And for the hardware direction, we wanted to develop specific components that implement a specific protocol function. And here we wanted to integrate high-level tools to optimize productivity within the hardware design flow. Furthermore, we wanted to look at protocol processing as a whole and optimize system level performance. So not only looking at the TCP layer alone, for example. One of these issues is, for example, an efficient and transparent integration within today's operating system. That does not require applications to be adapted. Let me now come to our TCP acceleration approach. You see here this layered architecture of today's TCP software stack. TCP IP is a relatively complex protocol. This stands for the general purpose processing engine. In that it has to support various networks, for example, mobile networks, wide area networks, or local area networks. Each of these environments have very specific properties, requirements, and so on. And since TCP has to work in each of these environments, it is definitely not optimized for high-end networks concepts to support all these kinds of networks. Another problem with TCP, instead of, for example, XTP, for example, there are many interdependent algorithms which share common state information, which share protocol headers, and so on. And this makes it difficult to do a hardware implementation. Another problem is that TCP is a relatively old protocol, and therefore oft implementations, for example, were often modified, adapted, and optimized, and therefore it's a bit difficult to understand and read this kind of implementation. And altogether, the complexity of TCP protocols is around 15,000 lines of C code. So it's obvious that a direct transformation towards hardware is not possible. And on the other hand, this would lead to a solution that is not very manageable and adaptable towards standard modifications, for instance. On the other hand, only a very small part of the TCP protocol has actual real-time requirements. The majority of the protocol is done for context management, for error recovery, and so on. And only a very small part, which we call taskbar, is responsible for user data transfer. So our idea was to develop a partitioning approach for the TCP protocol, where we can support only this fast path with specific hardware and the GPMS acceleration, and leave the remaining non-real-time processing on the software on the board. This kind of approach requires three things. First of all, a synchronization between the existing software TCP implementation and the acceleration, for example, with specific hardware. And therefore, after a connection is successfully established, one has to transfer the TCP context information towards the hardware partition. And if errors occur or the connection is about to be terminated, then this context information has to transfer back to the software implementation. Another thing that we wanted to achieve was operating system bypass to avoid the number of overhead categories that I described earlier in the talk. As I said, we can't restrict the networks we support to local area networks like gigabit Ethernet. And therefore, we also implemented a socket level switch that simply decides when to use the protocol acceleration support or not, based on the target of the connection. Let's have a closer look at what this fast path processing is about. As I said, it's only used for data exchange, so it consists of no connection management tasks. It does not do any error recovery, only error detection, and so on. And therefore, the complexity of this fast path is much smaller, and it's about only 10% of the overall TCP software stack. So this is the complexity that is actually doable with hardware support. Here we have a typical scenario where data is transferred in one direction. So we have the sender and the receiver with the TCP stack. The fast path consists of three major components. These are TCP send and acknowledgement, handling, and receive path processing. In this scenario, where data is exchanged in one direction only two of these components are active at each side. However, they share common context information like state variables and so on, and therefore synchronization has to be applied. developing hardware support for this complex transport layer protocols is a quite difficult thing to do, and therefore we started with a system simulation environment for complex communication systems. Here we wanted to use real operating systems and real application level software. We started with the flavor of the Linux operating system, which is that user mode Linux. This is a modification of the Linux kernel so that the entire Linux operating system can run within one process on top of the normal Linux operating system. So one is able to build virtual networks and virtual hosts on one PC alone. After having set up this user mode Linux processes, we added a network simulator to inject errors, for example. Afterwards, we applied the modifications that I described at the TCP layer and at the socket layer, and integrated specific simulators that run the fast path. For example, software, a CPU simulator, an instruction set architecture simulator that runs the fast path software version, and a VHDL simulator that runs the hardware implementation variant. Then we added a sample component for system evaluation, and which is meant to estimate system performance like throughput, delay, and so on, and helps us to detect potential bottlenecks. As I said, there are quite a number of end systems, and they are very heterogeneous and different. For example, if you think of a mobile phone for UMTS networks or of a file server, then each of these end systems has very different requirements towards protocol processing. For example, for file server, performance is of primary concern, while for mobile system, power consumption is very important too. So there's definitely no one-fits-all solution. This triggered us to have a look at very different implementation architectures, ranging from pure software to pure hardware. We started with support embedded RISC processors, which are often supported by standard operating systems like embedded versions of the Linux operating system, are supported by UC environment, and are therefore quite similar to develop compared to normal PC operating systems, the development for these kind of systems. Then we had a look at support intelligent network adapters, which are network adapters which also include embedded RISC processors. However, they usually do not offer operating systems, so the development is a bit more difficult. Then we had a look at network processors, where we have an Intel emulation board. This Intel network processor consists of 6 multi-threaded micro engines. So this gives us the opportunity to develop a fast path with parallelism in mind. However, these micro engines are only programmable at the assembly level. And last but not least, we're also looking at the development of specific hardware where we target FPGAs with a high-level design flow. One of these implementation architectures and targets I would like to describe now in more detail. This is a MirrorNet platform. MirrorNet is a packet communication and switching technology which is mainly targeted for high performance and highly reliable systems. So its main applications are system area networks and class interface. We see here the structure of the network adapter for this MirrorNet. In contrast to other network adapters for Ethernet, for example, which also consists of the PCI bridge, DMA controller, or the actual network interface, these intelligent network adapters add an embedded processor and local memory. So this embedded processor can be used for protocol processing. The development environment consists of a C compiler suite. However, there's no operating system, so synchronization primitives, for example, are not available. The processor only supports one context, so threads are not available, and the processor does not support interrupts. Myrinet comes with two important pieces of software, which are the host software called GM, which implements a message passing algorithm, and firmware, which is called MCP or Myrinet Control Program. Both of these software pieces are open source, so we could use them to modify them and integrate the fast pass here within this available software framework. For the implementation, we use the MCP, which consists of hardware-driven state machines, which handle mainly DMA controller programming, so it's the reservoir loader controller. We integrated the TCP fast pass within the network send and receive code, and took advantage of simple kind of hardware support for checksum computation. However, we did not do any specific optimization towards the processor architecture like assembly language coding or so, and the current implementation has some limitations. For example, we do not currently support the label algorithm, for example. What kind of band and performance levels can be achieved with this total file implementation? Here we have the normal PC system with 500 MHz, this Myrinet line adapter and Linux operating system, and the normal network benchmark application, which simply measures throughput and delay. The lowest graph shows the performance level that is achievable with the TCP software on the host. We achieve about 330 megabits, while for this lightweight protocol, which is the topmost graph, we achieve about 970 megabits. On the other hand, for the fast pass on the Myrinet adapter, we achieve bandwidth peaks in excess of 800 megabits, which is already quite good. In other words, if the message sizes grow and segmentation has to be applied, then this achievable performance drops to levels of about 600 megabits, which is still much better than the software implementation on the PC. And if you consider that this embedded processor runs at only 66 megahertz, then you see that there's quite a lot of potential for this approach if you think of other more advanced implementation architectures. I'm now concluding my talk. What I wanted to describe was an integrated architecture for protocol processing that we are developing at our university. This architecture consists of a design flow which integrates protocol analysis, partitioning, system simulation, development of various prototypes, optimizing them, and finally doing efficient operating system integration. Based on the simple prototype, I showed that this approach is both beneficial and may lead to major performance gains. This triggered a number of other work that we are currently doing. For example, we are about to finalize the work on a specific hardware implementation for the fast pass and an integration within a system on chip architecture, where we hope to gain throughput levels in excess of 200 megabytes per second. However, the overall goal will be to develop a flexible and configurable protocol engine based on this architecture, which enables one to set some kind of requirements and to derive a specific and optimized protocol engine based on these requirements. And that's where I'm working on automation support. Thank you very much.
Thanks a lot for this talk. Are there any questions from the audience towards Mirko?
Why do you not one of the main features of the performance for the
Okay, can you hear me now? Why do you use Linux and not one of the open source BSD variants based on BSD 4.4? Did you compare the performance?
Actually, we started with a TCP implementation for Windows NT, which was an IPv6 implementation of the Microsoft research department and then switched to Linux. First point is that Linux is more available than BSD, for example. The drawback is, however, that BSD TCP implementation is somewhat better structured. That's true. But there was a simple practical reason, because we have a Linux freak and not a BSD freak, so we took this direction.
Three different implementations.
Yes?
Yeah, this was like for BSD, I understand what wasn't available.
No, we have developed this approach only for Linux currently, and not for BSD operating system. So
Because it's not available? Because the free implementation of BSD is not available? That doesn't
No, that's not the point. It's just a question of effort that you have to put at this. And it's quite easy to develop just one platform and not many platforms. So we had to look only on the Linux operating system up to now, and not on other flavors, BSD, or I should say Sun or IBM platforms as well. It's just a question of effort.
Yes, but at least you could have done a comparison of the software performance without any hardware acceleration on a different operating system. It would be faster than the Linux, and you might not be using the right place to develop acceleration.
Maybe let me step in here. I think we can take this bit of the discussion offline, so the specialists can discuss that amongst themselves. Maybe that's more appropriate. Are there questions of a different nature which we could address right now? Maybe one more question. If not, we move on to the next speaker. Yes, one question.
You got the throughput numbers with very short debug times, very short turnaround. I don't know what to call it. Turnaround times. Have you ever thought of doing the same test with longer turnaround times?
With what?
I mean, with times of a few milliseconds.
Well, this is a local area network, the gigabit class performance, so one can expect run-through times below 100 microseconds, and not within the milliseconds ever.
Yeah, but over longer distances.
Yes, but we are currently looking only at local area networks, where this kind of performance is required and the network bandwidth is available, so that only, at least up to now, the acceleration approach makes sense within these areas. And if you think about area networks, they have only about 100 kilobytes per second or so, hardware support may not make much sense.
Thank you. Let me introduce the next speaker. It is Lothar Zier. He received his diploma in computer science from the University of Bonn in 1991 and joined the networking department of the German National Research Center for Information Technology, also known under the name of GMB after that. Currently is working on high-speed networking, especially optical switching in the net media group of the Institute for Media Communication of GMB. Floor is yours.
Okay. Do you hear me? Good afternoon, ladies and gentlemen. Okay? Better? I did this work together with my colleague Gundula Dörries. And what do we mean with high-speed multicast? It's a distribution of data to groups of receivers, of course, and we studied single multicast streams with more than 100 megabits per second. The outline of my talk is I will start with some challenges and risks of high-speed multicast. We'll introduce some practical technology, how you can implement such high-speed multicast distributions.
And we'll talk about some hotspots we find in our practical test environment, the gigabit test at West in Germany. At the end, I will give a short summary of the talk. The challenges. In the past, multicast started, I think Zier mentioned this, with broadcast multicast distribution on the Ethernet, yellow Ethernet cable, and it was a software-based multicast distribution with IP routers, with Unix workstations, normally using MRD. And this multicast distribution was restricted to only a few megabits per second. Now the situation has changed. New hardware, and this is correct for Ethernet switches, ATM switches, and also high-performance IP routers, support multicast distribution in hardware, and these machines can reach several hundreds or gigabits of gigabits with multicast traffic. The risk of this development is what we have called multicast disaster. If you start with a naive approach with high-speed multicast, you may find out that your server sends much less than you expect, but nevertheless your production network or parts of your production network is down, and your client doesn't even seem to receive much of the data. So the implementation goals for high-speed multicast is that the end systems should send and receive multicast with high data rates, and that the multicast distribution should be restricted inside the network, at best only to the interested receiver. Currently, there are 3 technologies available for a 100 megabit and more multicast distribution. There are 2 technologies, ATM and gigabit Ethernet, and of course there are 3 IP multicast router, which may connect layer 2 networks and which can be used to build up larger multicast networks. With ATM, ATM use so-called point-to-multipoint connections to distribute the data, and you may use this point-to-multipoint connection directly with a programming interface like WinSock 2 or XPI to build up point-to-multipoint connections and send data directly to receivers. The second possibility is to use LAN emulation, and at least for LAN emulation version 1 you have to use separate virtual LANs to distribute your multicast data, because LAN emulation uses broadcast mechanism. With gigabit Ethernet or Ethernet in general, it starts with a poor broadcast distribution of the multicast data, but today most switches implement IGMP snooping and send multicast data only to selected ports. Another method we use in our environment is to use, if you have rather fixed groups for high-speed multicast, you may use separate virtual LANs. This slide gives an overview about the theoretical limits you may reach on ATM 622 megabit lines and on gigabit Ethernet lines. The left column shows the protocols. XDI is the use of the native ATM connection. UDP LAN emulation is LAN emulation over ATM. And the last one is UDP gigabit Ethernet. The middle column shows the data payload. You have to add the additional overhead of the, for example, UDP and RT layer to get the correct packet size. And the right column shows the achievable throughput in megabits per second. What you can reach on the line is, or what you can see is that for small packets you get much fewer performance, of course, because the overhead is greater. And this goes down up to 188 megabits if you use LAN emulation in your network. For bigger packet sizes, you have typically around 530, 540 megabits on an ATM line and up to 964 megabits on a gigabit Ethernet. Our practical environment where we did our measurements was in the gigabit testbed West in Germany. We use as networking technologies ATM, gigabit Ethernet and IP routers, and as end systems Unix workstations from Sun and SGI. The network equipment was from Cisco and which is now Marconi. The software we used is based on the multi-generator or engine toolset. This was developed by the Naval Research Laboratory. It consists of some programs to generate and receive multicast traffic. On the slide is also the URL where you find the original software package. We did two extensions to the engine toolset. The first one, we implement a native ATM sender and receiver based on the XDI programming interface. And we also changed the buffer sizes to provide larger packets. This is an overview about our testbed, which we use for the multicast distribution. You can see ATM switches from Cisco, like the LS1010 and Catalyst 8540 MSR, and on 4. The Unix workstations use primarily ATM adapters from 4, but we have also some gigabit Ethernet adapters tested. The concrete scenario here is that we have a multicast distribution over LAN emulation. The Sun Ultra 60 called Gundula sends multicast data over a point-to-point connection to the bus, which is located on a Cisco Ethernet switch. And this bus distributes the data via point-to-multipoint connection to our clients. First, we studied sender performance and did measurements about the sending rate depending on the network technology and the packet sizes. We did tests for native ATM line emulation gigabit Ethernet and various the packet size from 50 bytes, not the packet size but the data payload from 50 bytes to 1472 bytes, which is a normal multicast payload for Ethernet packets. And it's supported. We use also higher data payloads like 8K kilobytes and 9,000 bytes. The maximum sending rate we found was 540 megabits for packets larger than 5,000 bytes with native ATM, a little bit fewer with line emulation, 510 megabits, and with gigabit Ethernet and smaller packets of 1472 bytes payload, 340 megabits. So the sending performance was limited for the first two by the link bandwidth and the theoretical limit, and by the later gigabit Ethernet limited by the standard performance. We also compared the technologies, and we found that gigabit Ethernet has is better for fixed packet rates. That means that it has a better implementation or lower overhead for a fixed packet size. The advantage of line emulation XPI in our environment was that they had better overall throughput because they can use bigger packet size. This slide shows the values for the native ATM send rate. You can see that for packets of 5,000 bytes and more, there is also the theoretical limit of around 540 megabits is reached, but for smaller packets the theoretical limit is not reached, but this sending rate is limited by the standard performance. This slide shows the three investigated technologies for a fixed packet size of with a data payload of 1472 bytes. For line emulation, the limit is around 190 to 200 megabits. For native ATM XPI, it's around 300 megabits, and for gigabit Ethernet, it's around 340 megabits. The difference between line emulation and XPI is caused by the additional protocol overhead of line emulation. The difference between XPI and gigabit Ethernet may have to do with hardware implementation, because the native ATM interface is a relatively simple, low overhead interface. One point with the distribution of multicast in line emulation networks, most line emulation networks use version 1, and in this network the multicast data is sent to a central bus, broadcast and unknown server, and is distributed with a broadcast mechanism to our client. Also, the sender itself is receiving this multicast data, and in the sender, this data is discarded by the ATM driver. We compared the multicast and unicast sending rate and to study this effect, and found that we get a smaller performance for the performance is around 20% lower than with unified traffic. This slide shows the values. You get 190 megabits with multicast and around 240 with kilocast. Studying the receiver performance, we found high data losses in overloaded receivers, and there are many techniques in the literature for improving the performance. We studied two of them, interrupt coalescing, where the network adapter aggregates packets before triggering an interrupt, and also increasing the UDP receive buffer size. Interrupt coalescing reduces the overall overload for the machine, and it reduces the receiver losses. For some machines that's considerably. We also found that increasing the UDP buffer size may help in some situations to smooth traffic leaks. Of course, or at least increasing the buffer size is no cure-all for slow receivers, but interrupt coalescing in our context is useful. This slide shows data losses without and with interrupt coalescing. The upper figure is without interrupt coalescing. The gray column shows losses in a relatively weak machine, Sankt Ultra 5. The black ones shows the losses in a more powerful machine, an Enterprise 250 server. We investigated 4 different sending rates, and this around 100 megabits, 170 megabits, 328 megabits, and 539 megabits. For the lower to lower sending rates, we use packets with payload of 1 kilobyte. For the higher sending rates, we use payloads with 8 kilobytes. The weak machine shows, if you don't use interrupt coalescing, loss rates of around 30 and 60%, and this means that have tremendous losses, and these losses don't happen in the network but in the receiver machine. With interrupt coalescing, you can reduce these data losses to nearly zero with 100 megabits and around 20% with 170%. You also can see the effect of large packet sizes, because a much higher receiving rate is achievable if you use large packets of 8 kilobytes. For larger networks, you have to use IP multicast routers, and IP multicast routing protocols are used for constructing distribution trees. There are 2 principles for constructing these trees. One is the flood and prune principle, where in regular intervals all multicast packets are flooded in the whole multicast backbone network, and after that this is pruned to a distribution tree where receivers exist in the network. Some popular multicast protocols, EVMRP and condense mode, uses this approach. These protocols are easy to implement and are supported by many vendors. The other method is explicit receiver registration, where data is only sent to receivers which have explicitly registered for the multicast probe. Fin's fast mode is such a protocol that uses this technique, and you should avoid using plug and prone protocols because they may cause severe traffic bursts in the whole multicast backbone network. Instead, you should use fast mode for as multicast protocol. We study or to demonstrate the effect of this burst, we have a sender which sends multicast, and this is around 320 megabits per second or 800,000 ATM cells. And in this network there was absolutely no receiver. And you can see that around all 3 minutes there is a burst caused by the Breiter and Kühn principle of around 3 seconds. And this burst happens in your complete network. This means if you have at any point in your multicast cloud slower routers with for example fast Ethernet or normal 10 megabit Ethernet interfaces, you may get severe problems. The general problem with UDP, especially UDP over multicast, is that you have no feedback mechanism for multicast sender in bottleneck situations. And this means that other traffic flows, especially TCP flows, may be severely damaged through the multicast distribution. There exist intelligent queuing mechanisms to reduce this congestion. For example, weighted pair queuing or RPC queuing in ATM switches. And this technique has the advantage that they allocate rather equal bandwidth between the traffic flows. The disadvantage of this technique is that they are expensive to implement in hardware. This RPC might improve the situation, and we study this in an example for a two-flow. For two flows, one is multicast flow which has around 800,000 ATM cells, and after a while we started a TCP flow, and you can see that multicast bandwidth is reduced and both flows get equal bandwidth. If there's no or if you use links with zones apart such techniques, you will find that the TCP flow or that the multicast flow doesn't change, and the TCP flow might get only the rest of the bandwidth. So summary, modern hardware allows high-speed multicast with hundreds of megabits per second, even for single multicast streams. And there are several technologies to realize that high-speed multicast in practice. We study ATM with native and use of native ATM connections and LAN emulation, gigabit Ethernet and IP routers. From a technical point of view, there's no clear winner. Maybe from another point of view, the clear winner is gigabit Ethernet and IP routers. And In this network, and this high-speed multicasting, traffic management is absolutely necessary. You have to use mechanisms to protect your unicast traffic, and such mechanisms are, for example, IGP smoothing or separate your multicast traffic in virtual LANs, or use more appropriate IP multicast routing protocols like Benz mode. From an application point of view, it's don't expect high data rates from small package, but you have to use large packets, and it may be useful to implement some kind of feedback mechanism to avoid receiver and network overloading. What data rates are today, or we did our test 1 year ago, realistic, 200 up to 500 megabits for test programs like Engine, and for applications, at least our concrete applications, we have radius about 100 megabits and below. Okay.
Thank you, Lothar. Are there any questions to him? Yes. Please use the microphone. Please.
Okay, the question is about the router you were using when you were doing the randomization tests. You said that the bad performance for the receiver was due to the packet discarding of the packets that were looping back. Can you tell me how loaded was the router when it was doing the work of the bus component? As I understand it takes quite a lot to forward the multicast.
What do you mean? The router or the bus?
You said you were running the bus component on the router.
No, the bus was running on a Cisco Ethernet switch. One general remark about performance. All these machines we use as a router the Cisco Catalyst 8540 MSR, and as a bus Cisco Catalyst 5000 switch. All these machines have hardware support for forwarding, and normally if you have the router load is nearly zero, because all this happens in hardware.
Okay, so
the performance of the router is, also the performance of the bus is around the line rate, and it may be restricted if you use small packets also by packets, but these are in the range of about 100,000 packets per second. And it's similar for the IP router. If there is hardware support, you get very good performance.
Okay, so it was hardware support and that was software component. Okay.
Okay, thanks a lot. More questions? Maybe we can take another one if there is one. If not, then let's go on with the next talk. First, I would like to ask the support to change the projection from the PC to that one. Okay, in the meantime, let me introduce our next speaker. It's Sabine Kühn. She received a diploma in computer science from the Dresden University of Technology in 1995. Since then, she has been a scientific staff member in computer science at the University of Dresden, and has done research on construction and deployment of resource reservations in advanced and high-performance networks, especially broadband integrated networks.
Thank you, Mr. Graf, for such a short introduction. In addition, I'd like to mention that the work I present you here is part of the project of the Research Association, joint TNC. We can name Federation Advanced High-Speed Network. This project is not only with routing with advanced or advanced federation, but also with the signaling, admission control, and general system behavior of such kind of federation. But before I speak on the actual topic, let's start with a short discussion. Why advanced federation? Well, as you know, in recent years, distributed multimedia division has received an increasing attention. These applications often require certain quality of service from network, for example, involved on packet delay, loss capability, and bandwidth. So to ensure the required quality of service level, there have been many proposals to support service differentiation. For the Internet, the most well-known approaches are the integrated services architecture, based on per-flow reservations, and on the other hand, the different service architecture which allows the better aggregation of reservations. Well, under this system, a new reservation can only be admitted if there are adequate free resources. This can lead to undesirable consequences. For example, real-time applications which involve many users. If we think on video conferences, lectures, games, etc., these applications often require a certain degree of planning, so that all participants are attending at the time in game time. So they noticed our rejected conferences due to a lack of resources often not accessible. So using advanced reservation accounting would solve this problem. Furthermore, we think on trunk network capacities, there's an increasing demand for long-term planning. For example, provided by virtual design or virtual private network. So providing an automated backup of an advanced reservation would eliminate the manual configuration efforts at the routers along the selected path. To meet the demand for planning resources over time, we have explored support for advanced reservation. So in the following, I present you a general model dealing with the in-time parameters, and subsequently I show you the impact of advanced reservation as a result of the numerical analysis. With this simple model, we define phases, even time, I can't show you anything, sorry, and related actions which are required as part of an advanced reservation. At the beginning of the negotiation phase, we have to specify at what time and how long we intend to reserve. In contrast to immediate reservation or traditional reservation, the duration parameter is required to ensure that such reservations are not preempted by earlier booked or later beginning reservations. So, within the negotiation phase, a routing path is established, and the request is negotiated as on the conventional stage. The only difference is that after a successful emission control along this path, the observation is not performed immediately, but the resources are virtually reserved for the point of time when the connection is actually used on the application. So before a connection is to be activated by the user in the initialization time, the connection parameters or state might be changed by the user. This concerns, for example, the time parameters as well as traffic parameters and or even the cancellation of the reservation. Assuming that the connection or reservation is still available and there's no activation performed in the specified time interval, then the pre-allocated resources are reached and are available for other connections. Okay, so far the basic about the general model is used to expand the resource preservation protocol of RCP and the able signal and advanced preservation. To get more insight in the behavior of an advanced preservation system in view of the suitable quality of service-based routing and emission control, we have analyzed a discrete time loss system using multiple chains. A discrete time model was used because in general dates are made in steps of 5 up to 30 minutes. The choice of the slot time, however, is an important decision that affects in the design of the reservation and affects the performance, the network performance, or exporting or occupancy, and on the other hand, the administrative scope and the effort of the emission control. Well, for the sake of simplicity, we assume that each reservation only requests one of n channels. That means we only consider homogeneous band requests. Moreover, we assume that the service time of reservations to be geometrically distributed, and on the other hand, the arrival process and the distribution of starting time can be of arbitrary nature. Based on this model, which is described in more detail in our paper, we defined or we identified a number of performance parameters, such as the blocking probability, depending on service time and time booked ahead, throughput and visualization, and mean service time of successful reservation. Now I proceed with some results which are substantial for the new working algorithms. Let us now consider the characteristics of a pure advanced reservation system. I'll concentrate here on this one on the results we have obtained for one system, namely a group of 50 channels as Poisson distributed service time, Poisson distributed arrival time with mean value lambda, you can see, per slot, and with the slot size should we know that the average service time is of 10 slots. And finally, with the reservation of 98 slots. The left figure now shows the locking probability of a call of node interval m, that means that booked m slots in advance. That this function is a decreasing one. That means an advanced reservation that shall be projected or shall be reported if there are only a few requests which have been earlier. In contrast to a traditional system of reservation system, the blocking probability depends on the duration of an advanced reservation. So we have different blocking probabilities. The blocking probability at the starting point, the middle one, and the probability that any slot is occupied, or that all channels are occupied in any other slot of the duration. The impact of the latter one, latter probability, is shown on the right hand. Here we can see that the average service time goes down to the zero fraction of the non-reservation. And this because there's a higher fraction of advanced reservation at the beginning of the reservation book. It means if resources are scarce, then advanced reservation results in some presentation of time. So there's a greater chance that the requests for short duration are accepted if they have not so strong in advance. However, it's not easy for the user to decide when or how early he has to book, because this depends not at least on the behavior of other users. But what we can say for sure is that the chance the reservation is accepted increases with the booking ahead time. We now compare the blocking probabilities of different systems by wearing the reservation book line. The figure on the left hand shows that the overall blocking probability is nearly independent of the reservation book line. The blocking probability at the starting point, however, decreases significantly with the length of the reservation book, and at the same time the blocking probability during the duration increases. The associated rising presentation of the latter probability is then to a decreased system utilization shown on the right hand. So far, the basic for advanced reservation, I now deal with the question how can we use the results and the insights of our numerical analysis to make routing decisions for advanced reservation, and how can we achieve a good trade-off between cost, for example, in terms of maintenance, and performance assessment. But first, some aspects of quality of service routing. In contrast to traditional routing, quality of service based routing uses specific parameters like the available bandwidth and application-specific information like the requested bandwidth to make an appropriate path selection. So the benefits of quality of service routing relate to an improvement of the services the user receives and on network utilization. The quality of service-based routing implies that each node has to maintain a database where all relevant quality and link information is stored. The accuracy of data within the basis depends on the distribution of changed link state information, and that means on the sensitivity of the trigger quality, which can be based, for example, on thresholds shown on the right side, and on regular time intervals. Clearly, when the sensitivity of the trigger quality is reduced, so are the accuracy of information in each router and the network or network load. As a result of simulation studies found in the literature has been shown that the shortest path is on the right hand. The shortest path algorithm performs better than the widest path heuristic. So in view of network performance, the shortest path with respect to the number of hops is chosen from a set of all visible passes in your network. For later comparison with our algorithm, which I explain on the next slide, we use the widest shortest path algorithm for advanced reservation as we expected that it performs or has best network performance if we assume that all link state information on each router is known. So we consider two cases. In the first case, changes of the future link states are updated immediately. So we can exactly determine whether or not a new reservation will be or can be accepted on all of the paths. If there are more than one short path available, then this one is the most available best to the meaning of widest. In the second case, link states are periodically updated after a specific time interval to reduce protocol overhead. But the use of the widest shortest heuristic seems not to be practical with respect to advanced reservations if you have a look on the maintenance effort. In this table, we can see that the administration effort can grow extremely depending on the number of links and on the number of entries in the reservation book. For example, if we have 100 links in a routing domain and a reservation book length of 80,000 slots, then we have to maintain approximately 60 megabytes in each router. That's why the basic idea of our algorithm is that we only need a few link-specific parameters and that we are able to evaluate the link state probability for this starting point. The parameters we need are the load of arriving advanced reservations on each link, the link capacity, and finally the administrative reservation book length. The load can be calculated by measuring the intensity of arriving reservations and the mean duration of such calls, and will then be distributed by the routing protocol. To calculate now the state probabilities of a given link, we use a single approximation of our numerical analysis. Based on the results of this model, we can say that the state probability can be approximated, state distribution can be approximated by Poisson distribution with the mean value of rho. Moreover, we know that the load depends on the capital starting point, and it is discrete or can be expressed by a discrete function or like a simple one. Now we can approximate the probability for the starting point, which is expressed that all channels are occupied during this point of time, and we use this probability as a routing matrix for the time selection process. Because of the fact that we deal with probability, we are not able to decide if there are actual not available not enough values on a given time. So this has two consequences. At first, a call might be misrouted. So we use a transback mechanism to route the request on an alienated path. The second consequence is that we have to restrict at this stage our algorithm to the set of critical shortest paths. At last, we have considered a sub-algorithm called TNC2001 that randomly routes the request over the set of shortest paths. To compare these algorithms, we have used simulations, which we have conducted in various topologies. So the first topology, we have used a symmetric network shown on the left side. In this topology, there exists more than one shortest path, a typical shortest path between each source destination pair. So we have nearly the same conditions for all algorithms in selecting a path. A more realistic model topology is shown on the right hand. This is an unsymmetrical topology, and in contrast to the left one, there are seldom several short paths between each destination and source. We have chosen this topology to analyze the efficiency of the routing algorithms in the context of a real environment. In both topologies, we have basically an incapacity, unevenly distributed traffic profile, and finally we have chosen the value of the duration and the arrival rate in such a way that we have a likely local network. We now compare this algorithm in terms of blocking probability. In this figure we can see the blocking probability of the widest shortest path with accurate information. It means that the changes of link states are distributed immediately, and the blocking probability where the escape interval is of 10 blocks. We can see that the differences between both functions become significantly smaller as the fraction of the one observation grows. The reason is that the more or the higher the fraction of advanced observation, the more the changes of states are distributed over time. So it becomes more unlikely that significant changes for a specific point in time. The misorbit request includes both those routed but rejected by machine control and those not routed by the physical function actually exist. The random route algorithms perform very poorly, but the blocking probability can be significantly decreased if we allow only one kind effect for advanced operations. The interesting point here in this scenario is that our algorithms have a significantly better performance than the wide shortest path with inaccurate but pulling the same information. If we allow transvection mechanism related to our algorithm, then we achieve surprisingly nearly the same performance as the widest shortest path with accurate information. In the second topology, the advantage of the widest shortest path becomes more obvious. That is because our algorithm only uses the physically shortened path, whereas the widest shortest path Kühn going where the available bandwidth is less than the required one. So the algorithm selects that shortest path in the remaining step. But if the information base is inaccurate of the widest shortest path, then the difference between that one and ours depends on the fraction consideration. Let me now give you a short summary. Also, while the short term is accurate information has always best performance in terms of blocking probability and throughput, the effort to maintenance looks extremely with the use of advanced algorithms. This applies also in view of the protocol overhead as shown in the table. Whereas our algorithm only needs to distribute changes of the average slope to be distributed for the widest possible path. All link state information for all reservation group entries must be included. As you can see in the table, the protocol overhead grows with the fraction of one reservation and clearly with the reservation group length and the intensity of the arrival in one reservation. Using a nested interval of 10 slots, then the routing overhead can be used. But overall, we conclude that the use of one short path seems to be less effective, like in for non-reservation, whether or not the base database is effective or not. In view of likely loaded in a looked method like quality two, the efficiency of our algorithm can be improved if there's no restriction to physically short paths. This can be done by using thresholds for the link matrix, but this is not our type. Thank you.
Thank you very much, Sabine Kühn. Questions from the audience? No questions, that looks like? Okay. So, that concludes this session. Just let me remind that the buses leave here in almost quarter of an hour, so that will be 5:45. They will pick you up at the hotel at 6:30. Have a nice evening.